I'm Dave Anderson. In this video, I'll talk about game theory, which is about the strategies of players in many types of games. If you play sports, you know the importance of strategies. Businesses also use strategies, as will you in the game of life. I'm going to explain payoff matrices, the prisoner's dilemma, dominant strategies, and Nash equilibria. The payoff matrix shows the outcomes, or payoffs, for each of the players depending on the combination of strategies chosen. The left column shows the possible strategies for player 1, strategy A and strategy B. For a business, strategy A might be charging a high price and strategy B might be charging a low price. The top row shows the possible strategies for player 2. Again, strategy A and strategy B. The numbers in the boxes are the payoffs. The payoffs on the left are for player 1. The payoffs on the right are for player 2. The set of payoffs received depends on the strategies chosen by each player. If both players choose strategy A, the payoffs are in the upper left box of numbers. If player 1 chooses strategy A and player 2 chooses strategy B, the payoffs are in the upper right box of numbers. If player 1 chooses strategy B and player 2 chooses strategy A, the payoffs are in the lower left box of numbers. And if both players choose strategy B, the payoffs are in the lower right box. A classic game in game theory is the prisoner's dilemma, in which two players, we'll call them Chris and Pat, are apprehended after a crime. They did commit the crime, but there's not a lot of evidence against them, so the police put them in separate rooms and interrogate them. They must each decide whether to confess to the crime or to deny involvement in the crime. In this game, the numbers in the payoff matrix represent the number of years the criminals will have to spend in prison, so a lower number is better than a higher number. If they both confess to the crime, Chris and Pat will each spend 5 years in prison. If they both deny committing the crime, the sentence will be shorter, 2 years, because there isn't a lot of evidence against them. If Pat confesses to the crime and Chris denies involvement, Pat will get a light 1-year sentence for his honesty and his help convicting Chris, while Chris will get a heavy 10-year sentence for being a lying denier. In the opposite situation, Chris will get a light 1-year sentence and Pat will spend 10 years in prison. A player has a dominant strategy if the same strategy is best for that player regardless of the other player's strategy. You can use the circle trick to find dominant strategies. To employ the circle trick, we put a circle around the best outcome for each player based on what the other player might do. For example, suppose that Pat confesses. Chris gets 5 years by confessing, 10 years by denying. The best outcome for him is 5 from confessing. If Pat denies, the best outcome for Chris is 1 from confessing. So we circle the 1. 2 circles in the same row for Chris indicates that he has a dominant strategy. Chris's dominant strategy is to confess, because he has 2 circles in the confess row. Now let's check Pat's options. If Chris confesses, Pat gets 5 years from confessing and 10 years from denying. We place a circle around the best outcome of 5 years. If Chris denies, Pat gets 1 year from confessing and 2 years from denying. So we place a circle around the best outcome of 1. 2 circles in the same column for Pat indicates a dominant strategy. Pat has a dominant strategy of confessing because there are 2 circles in the confess column for him. Now let's look into Nash equilibria. A set of strategies is a Nash equilibrium if neither player wants to switch strategies given what the other player is doing. The circle trick for finding a Nash equilibrium is to find 2 circles in the same square. In our prisoner's dilemma example, there are 2 circles in the box that represents each side confessing, so this is a Nash equilibrium. To see why, notice that given that Chris confesses, Pat doesn't want to switch from confessing to denying because his time in prison would increase from 5 to 10 years. And given that Pat confesses, Chris doesn't want to switch from confessing to denying because his time in prison would increase from 5 to 10 years. So the 2 circles in the box that represents each side confessing is a Nash equilibrium. Gerard Piqué is a soccer player. He really likes going to soccer games. Shakira is a singer, and she really likes going to concerts. They also like each other. Suppose that they had agreed to go to either a concert or a soccer game, but they can't remember where they agreed to meet, and they're separated. They don't have good cell service. They each have to decide which place to go to.
This game is called the Battle of the Sexes, and the numbers in the payoff matrix represent the levels of happiness or utility each player receives depending on the outcome. If they both decide to go to the concert, they're happier than if they were apart, and Shakira is particularly happy because she likes going to concerts a lot. If they both decide to go to the soccer game, they're again happier than if they were apart, and Gerard is particularly happy because he's a big soccer fan. If Gerard goes to the game and Shakira goes to the concert, they're not as happy as if they were together, but happier than if they went to the event they liked the least. If they each go to the event they like the least, thinking wrongly that the other would be there, this produces the worst outcome for both players. Let's check the options for Gerard. If Shakira goes to the concert, Gerard is better off at the concert, so we circle the best outcome in that case of 20. If Shakira goes to the game, Gerard is better off at the game, so we circle the best outcome of 40. Checking Shakira's options, if Gerard goes to the concert, Shakira is better off at the concert, so we circle her best outcome in that case of 30. And if Gerard goes to the game, Shakira is better off at the game, so we circle her best outcome of 27. We see that there are two circles in both of the boxes representing the players being in the same place. So there are two Nash equilibria. One is both players going to the concert, and the other is both players going to the game. That makes sense because if they're both in the same place, neither one wants to independently go to the other place.
Suppose the titans of the bagel industry, Bagels Now and Tiny Bagels, both want to open a bagel shop in the same town, but the town's not big enough for both of them.
In this first mover advantage game, the payoffs are profits in thousands of dollars, or, if they are negative, losses. If they both open a bagel shop, they divide the bagel customers between them, and they both lose money. If neither company opens a shop in the town, neither company earns any profit. If only Tiny Bagels opens a shop, they have enough customers to earn a profit. Likewise, if only Bagels Now opens a shop, they will earn a profit. To employ the circle trick, you can start by looking from the perspective of Tiny Bagels and suppose that Bagels Now opens a shop. Circle the best outcome of 0 profit, which is better than losing $2,000 per month. You try the rest. You can pause the video now and look for any dominant strategies or Nash equilibria, then restart the video to see the answers. In this game, there are no dominant strategies because there aren't two circles in the same row for Tiny Bagels or in the same column for Bagels Now. There are two Nash equilibria. One is just Tiny Bagels opening a shop, and the other is just Bagels Now opening a shop.
Few people know that Abraham Lincoln and his wife, Mary Todd Lincoln, liked to play a game where they would each choose heads or tails on a penny, and then they would each gain or lose a penny depending on the combination of the strategies chosen.
Here's the payoff matrix for the matching pennies game. If the pennies matched, Abraham would lose a penny to Mary. If the pennies didn't match, Mary would lose a penny to Abraham. You can pause the video now and try to find any dominant strategies or Nash equilibria in this game. Here's what your payoff matrix should look like after doing the circle trick. In this game, there are no dominant strategies and no Nash equilibria. Here's a game called Chicken, played by Dumb and Dumber. In this game, the two dumb players drive toward each other and then either continue to drive straight or swerve. The numbers in the payoff matrix represent levels of happiness or utility. If they both continue to drive straight, they both end up badly hurt and very unhappy, to say the least. If they both swerve, they neither gain nor lose any utility as a result of the game. But if one swerves and the other doesn't, the one who swerved loses utility and the one who went straight gains utility. This game has no dominant strategies and two Nash equilibria, both of which involve one player swerving and the other player going straight. Now you've learned to analyze some games of strategy without being dumb or dumber. If you haven't had enough fun yet, check out the two bonus games at the end of this video.
In the advertising game, J-Mart and Tall Mart